Hi all. I'm going to discuss the root locus method, which is a graphical method for checking the stability of a system. In a control system, if you wanted to check the stability, one of the method for checking the stability is root locus method. So in root locus method, as already I mentioned, it is a graphical method. There are certain steps involved in the graphical method. So coming to the step number one. So first step is write the open loop transfer function. So in order to write the open loop transfer function, it is very simple. It is the product of all the transfer function in the block diagram. So if you are considering process, measuring element, controller and final control element, the overall transfer function is the product of transfer function of individual units. So that we can represent it with the letter G. So normally that will be given in the question. So G is equal to, we can write it in the form of Kn by D or K equal to S minus Z1 into S minus Z2 etc. up to S minus Z term divided by S minus P1 into S minus P2 into etc. up to S minus Pn. Next is, if you equate the denominator to 0, you will be getting poles, and if you equate the numerator to 0, you will be getting zeros. So there are two terms in the root locus diagram. So one is poles and the other one is zeros. The poles are representing it with the letter P. In graph, it will be representing it with the symbol star, and zeros can be represented with the letter Z, and it is representing it with the symbol circle in the diagram. So coming to a question, in question they are giving the open loop transfer function directly. So first write the open loop transfer function and the equate numerator to 0 and equate denominator to 0. So when you look on to this question, the numerator doesn't have any S value. So no, we can say that it is having, there is no zeros. And when you look onto the denominator is a polynomial, third order polynomial equation. And from that it is clear that three poles will be there. So we have to find the values of poles. So for finding the values of poles, what you have to do is, you have to equate the denominator to 0. S equal to 0. So that is one value. Then next equate this S square plus 6s plus 25 equal to 0. So by solving this equation by using a quadratic equation, we will be getting two solution. So one is minus 3 plus 4i and the another one is minus 3 minus 4i. So therefore I can write, so I have three poles. So one is P1 is equal to 0 and the other one is P2 is equal to minus 3 plus 4i and minus 3 minus 4i. So one more thing is there. So the number of poles are normally representing it with the letter N. So here we are getting 3 poles. So therefore N equal to 3. Another thing is number of zeros normally representing it with the letter M. And here there is no zeros. So therefore M equal to 0. So moving on to the rule number 2. So, according to the second step, the number of poles is equal to number of branches. So, in our case, so we are having 3 poles. So, definitely 3 branches will be there. Another thing is, all the branches will start at poles and terminate at zeros. എല്ലാ ബ്രാഞ്ചുകളും സ്റ്റാർട്ട് ചെയ്യുന്നത് പോൾസിൽ നിന്നാണ്, ടെർമിനേറ്റ് ചെയ്യുന്നത് സീറോസിലാണ്. ഇനി n minus m branches will terminate at a zero infinity. അതായത് 3, in our question we are having 3 poles and number of pole is 3. So 3 minus m equal to 0. So 3. So 3 branches will terminate at a zero infinity. അപ്പം പല ബ്രാഞ്ചുകൾ ഉണ്ടാകും. ഈ ബ്രാഞ്ചുകൾ ടെർമിനേറ്റ് ചെയ്യുന്നത് സീറോ ഇൻഫിനിറ്റിയിലായിരിക്കും n minus m branches. So coming to the our graphical representation. So in order to plot the graph, first thing is you have to mark the real axis and the imaginary axis. So this is the real axis. We know the real axis. We can mark it as 0, 1, 2, 3 to the right side, and -1, -2, -3, etc. to the left side. Next is if imaginary axis. In order to mark the values of imaginary axis, so I have marked it as I, 2i, 3i, 4i, 5i above 0, and -i, -2i, -3i, -4i, 5, -5i below the 0. So next is I'm going to mark the poles. So first pole is P1 equal to 0. So that I marked with a cross symbol. And P2 is -3 plus 4i. So that I marked here. And -3 minus 4i that I marked below 0. So that will be here. So first I marked all the three poles. So so I'm getting one more information. So there will be three branches, and all the branches will start at poles and terminate at 0 infinity, because here there is no zeros. So therefore all the branches will terminate at infinity. So moving on to the rule number 3, real axis is a part of a locus diagram. So after marking the poles, so we wanted to check whether this real axis is a part of a locus diagram. So for checking this, so I will be considering a test point somewhere on the real axis. Suppose I am considering a test point here. Test point here, to the right of a point, how many number of poles and zeros? Count and take the sum. If it is an odd number, then that part is a part of a real axis, is a part of a locus diagram. So when you consider here, so if I consider the point to the right side of 0, so there is no poles and zeros, so therefore that part is not a part of a locus diagram. So when I consider a test point here, to the right of this point, so one pole is present, so which is an odd number, so therefore this part is a part of a locus diagram, and so that I highlighted with a blue pen. So once again I can explain, അതായത് റിയൽ ആക്സിസ് ലോക്കസിന്റെ പാർട്ട് ആണോ എന്ന് അറിയാൻ വേണ്ടി നിങ്ങൾ ഏതെങ്കിലും ഒരു ടെസ്റ്റ് പോയിന്റ് റിയൽ ആക്സിസിൽ പിടിക്കുക. ആ പോയിന്റ് പിടിച്ചു കഴിഞ്ഞാൽ ആ പോയിന്റിന്റെ റൈറ്റില് എത്ര പോൾസും എത്ര സീറോസും ഉണ്ടെന്ന് കൗണ്ട് ചെയ്യുക. അത് ഓഡ് നമ്പർ ആണെങ്കിൽ, ആ നമ്പർ എന്ന് പറയുന്നത് ഓഡ് നമ്പർ ആണെങ്കിൽ, സോ ദാറ്റ് പാർട്ട് ഈസ് എ പാർട്ട് ഓഫ് എ ലോക്കസ് ഡയഗ്രാം. അതർവൈസ് that is not a part of a locus diagram. Okay, and another thing is, here we are having poles, complex poles. അതായത് P2, P3 എന്ന് പറയുന്നത് കോംപ്ലക്സ് പോൾസ് ആണ്. ഓക്കെ, സോ ഇറ്റ് ഈസ് നെസസറി ടു കൺസിഡർ ഓൺലി ദ റിയൽ പോൾസ് ആൻഡ് സീറോസ് വൈൽ അപ്ലൈയിങ് ദിസ് റൂൾ. സോ നോ നീഡ് ഫോർ കൺസിഡറിങ് ദ complex poles and complex zeros. Another thing is, if there is an nth order pole or zero, it must be counted n times while applying this rule. Suppose you are having a square in the denominator. So that means s equal to 0, s equal to 0. S is having two values. So at that time, that should be counted 2 times. So that is the meaning. Okay, so after marking the real axis is a part of a locus diagram, so this part is a part of a locus diagram. Next, moving on to the third rule, asymptotes. So before drawing the original locus diagram, we'll plot a asymptotes. Asymptotes means it is a ruparekha. Okay, so asymptotes, there are n minus m branches asymptotically approach straight lines radiating from the center of gravity of the poles and zeros of the open loop transfer function. Okay, so first thing is, you have to find the center of gravity of all these poles and zeros. So from this center of gravity, certain asymptotic lines radiates, which makes a particular angle of theta is equal to 2k plus 1 into pi divided by n minus m, and these are straight lines. Okay, so we are getting some information after plotting the asymptotes. So we are getting an information about how the locus looks. Okay, so in order to find the center of gravity in this question, so center of gravity or centroid, which can be represented with the letter gamma, sum of poles minus sum of zeros divided by n minus m. So I substituted all the values and finally I am getting center of gravity is minus 2. Angle, I have calculated it as 2k plus 1 into pi divided by again n minus m. N minus m in this question it is 3. And the k value which goes from 0, 1, 2, etc. up to n minus m minus 1. So, n minus m minus 1 means 0, 1, 2, etc. up to 3 minus 1. So, that is 2. So, you have to substitute the value of k as 0, 1, 2. So, after substituting the k value 0, 1, 2, I am getting the angle of pi by 3, pi, 5 pi by 3. So that I can mark it on the graph. That is center of gravity I am getting minus 2. So that I am marking it as here. So this is center of gravity. And from the center of gravity I have to draw 3 asymptotic lines because n minus m is 3. So 3 asymptotic lines and those asymptotic lines makes an angle of pi by 3. Pi by 3 means 60 degree. Then pi 180 degree. 5 pi by 3. 5 pi by 3. So that is that also has to be marked. So in order to mark the or draw the asymptotic lines, so you place a protractor here, find 60 degree and mark here and draw a line, draw a dotted line. So by using the protractor, so we can mark the asymptotic lines. Asymptotic lines are representing it with the dotted lines. So one is this one, 60 degree, that is pi by 3. So another one is 180 degree here itself, so that we cannot see. And another one is 5 pi by 3, so that will be here. So in that way, we can mark the asymptotic lines. So next is rule number 5, breakaway and break-in point. When two poles come closer on the real axis, there will be a breakaway point, and when two zeros come closer on the real axis, there will be a break-in point. So breakaway or break-in point we can find by using two methods. So one is, if you write the equation, the summation of 1 by s minus zi equal to the summation of 1 by s minus pj, or by solving this you will be getting an s value. So by using that s value, we can mark the breakaway or break-in point. Or another way is, first write the characteristic equation, that is 1 plus gh of s is equal to 0, and find k equation and differentiate the equation dk by ds equal to 0 and find s value. So in this way, we can find the breakaway or break-in point. But coming to this question, so here we are having only one pole on the real axis. So there is no pair of poles on the real axis, or there is no zeros. So therefore, we can say there won't be any breakaway or break-in point in this question. Next, moving on to the rule number 6, angle of departure and angle of approach. So, when a pair of zeros are complex, so there will be an angle of approach, and when a pair of poles are complex, there will be an angle of departure. So already initially we mentioned that is all the poles, all the branches start at poles. എല്ലാ ബ്രാഞ്ചും സ്റ്റാർട്ട് ചെയ്യുന്നത് പോൾസിൽ നിന്നാണ്. അപ്പം രണ്ട് പോൾസ് കോംപ്ലക്സ് ആണെങ്കിൽ ആ ബ്രാഞ്ചസ് എങ്ങനെയാണ് ഡിപ്പാർച്ചർ ചെയ്യുന്നത് പോൾസിൽ നിന്ന്, ബൈ മേക്കിംഗ് ആൻ ആംഗിൾ. ആ ആംഗിളിനെയാണ് ആംഗിൾ ഓഫ് ഡിപ്പാർച്ചർ എന്ന് പറയുന്നത്. So there is a formula for finding angle of departure and angle of approach. 180, if you wanted to find theta d, angle of departure, 180 plus sum of the angle made by zeros minus sum of the angle made by poles. Suppose if you wanted to find the angle of approach theta A, it will be 180 minus sum of the angle made by zeros plus sum of the angle made by poles. Coming to our question, so we are having two poles are complex poles. So there will be an angle of departure. So in order to find the angle of departure, so what you have to do is pick the complex pole. ഏതെങ്കിലും ഒരു pole fix ചെയ്യുക. Okay. So suppose I am considering P2. ആ P2 ന്ന് ബാക്കിയുള്ള എല്ലാ പോൾസിലേക്കും സീറോസിലേക്കും ഒരു ലൈൻ വരക്കുക. Okay. So from P2 to P1, I can draw a line. From P2 to P3, another line. Okay. Zeros ഇല്ല. Okay. എന്നിട്ട് what you have to do is you have to measure the angle made by the horizontal. That line made by the horizontal. ഈ ആംഗിൾ മെഷർ ചെയ്യാൻ നേരത്ത് കിട്ടുന്നത് 127 ഡിഗ്രി. So when I measure P2 to P3, ഇത് ഹൊറിസോണ്ടലുമായിട്ട് ഉണ്ടാക്കുന്ന ആംഗിൾ 90 ഡിഗ്രി. So I am getting two angles. One is 127, another one is 90 degree. So this value, when I substitute into the equation, 180 minus sum of the angle made by poles, that is 127 plus 90, plus sum of the angle made by zeros, it will be 0. So therefore, totally I am getting an angle of minus 37 degree. So what I can do is, so here, so we are getting the angle of departure as minus 37 degree. So in order to mark the angle of departure, or in order to mark the angle of departure on the graph, so what you have to do is you place a protractor here and mark a negative 37. So it will be below this point. So almost it will be here. So mark that point and draw a line. So, and one more thing is, so this root locus diagram, root locus lines, it will be moving parallel to the asymptotic lines. അപ്പൊ അത് വെച്ചിട്ട് നമുക്ക് ഈ ലൈൻസ് വരക്കാൻ പറ്റും. So the lines will be like this because we know this is our asymptotic lines. അപ്പൊ asymptotic linesന് parallel ആയിട്ട് minus 30 theta d, അതായത് minus 37 ഡിഗ്രി ആംഗിൾ ഓഫ് ഡിപ്പാർച്ചറിൽ ഈ ലൈൻ ഇവിടെ നിന്ന് ഡിപ്പാർച്ചർ ചെയ്ത് അസിംപ്റ്റോട്ടിക് ലൈനിന് പാരലൽ ആയിട്ട് പോകും. Okay, so here also it will be the same way. Another thing is, so when you look on to the diagram, so it will be a mirror image. അപ്പൊ നിങ്ങൾ ടോപ്പ് പോർഷൻ വരച്ചു കഴിഞ്ഞാൽ അതിന്റെ നേരെ മിറർ ഇമേജ് വരച്ചാൽ മതി ബോട്ടം പോർഷനിൽ. Okay. Another thing is, so here this root locus lines, so it will be crossing the imaginary axis. So in order to find the crossing point, so we can use Routh-Hurwitz criteria. It is already discussed. So crossing the imaginary axis, apply the Routh-Hurwitz criteria. First write the characteristic equation and make Routh array and find the k value. So at k is less than 150, the system will be stable. At k equal to 150, the system is on the verge of instability. So next is, so in order to find where the root locus line crosses the imaginary axis, what you have to do is consider the nth row and write the characteristic write the equation as cs square plus d equal to 0. So here it will be cs square plus d equal to 0, cs square plus k we are getting 150. So substitute and find the s value. Yes, we are getting plus or minus 5y. So that we can mark it here. This is plus 5y and this is minus 5y. So when you draw the locus line, so draw a line with the theta d minus 37 departure angle and draw the root locus and which crosses 5y and draw the line parallel to the asymptotic lines. So above 0 and below 0, the same way we can plot the diagram. So this is actually the root locus diagram and we can check the stability by using Routh-Hurwitz root locus diagram. So we can say at poles for poles, k value will be 0. At zeros, k value will be infinity. So when you look onto this branch, k equal to 0 here, and k value increases, and when it reaches to infinity, k is infinity. So here all the roots lies on the left half plane. So therefore the system is stable. But when you look onto the other two branches, so one branch start at P2, k equal to 0 here, and when k increases, and when at k equal to 150, so that we calculated, at k equal to 150, the system is on the threshold of instability. When k greater than 150, the system is unstable. So here also like that, when k equal to 0, stable, up to k value 150, the system is stable. Above k equal to k 150, the system is unstable. So with this I conclude.